If you look at the physical mechanics of the modern world, you quickly realize how much of your daily life depends on thousands of tons of metal sliding across the ocean. The phone in your pocket, the clothes you wear, the parts inside your car. Nearly every object we touch originates in a factory thousands of miles away and arrives with clockwork precision. Society looks to the microchip as the defining innovation of our age, but the packed geometry of this terminal proves that the global economy relies on the logic of the steel box. To understand why that box matters, we have to look at the world before it existed. In 1950, international trade was surprisingly stagnant. Relative to the size of its economy, the United States was actually trading less than it had during the Great Depression. Moving goods was so difficult and expensive that it rarely made financial sense to ship products halfway across the country, let alone across an ocean. This physical friction trapped economies and local markets, leaving global trade restricted and inefficient. The problem was a method called break-bulk cargo. Instead of moving items in bulk, ships carried thousands of loose objects, crates, barrels, steel coils, and sacks of sugar, all jumbled together in a single shipment. Loading these ships required armies of longshoremen to physically haul every single item down into the cramped hull. They played a manual game of Tetris, weaving delicate wooden crates against heavy steel drums so the cargo wouldn't shift and capsize the ship in open water. This chart breaks down the journey of a typical cargo ship, the Warrior, in 1954. It carried nearly 200,000 individual items from New York to Germany. The data reveals a massive bottleneck. The vessel spent a full half of its total voyage time simply sitting at the dock, waiting for humans to load and unload it piece by piece. When we convert that lost time into dollars, we see that cargo handling alone consumed nearly 40% of the entire shipping budget. The sea voyage itself was efficient, but the physical transfer of goods to and from land was draining the industry. The maritime industry was suffocating its own potential by optimizing the wrong variables. Companies built faster ships, but a faster ship just reached the next pier sooner, only to sit paralyzed for another week. Railroads and shipping lines had tried putting freight into boxes for decades, but those early attempts did not change the economics of shipping, because operators treated the boxes like regular loose cargo, wedging them into holes alongside barrels and sacks. The solution required an outsider. Malcolm McLean ran a successful trucking company in North Carolina, and he viewed the logistics problem through a completely different lens. McLean recognized that his business was moving freight at the lowest possible cost. The ships were merely equipment used in that process. To eliminate the dockside bottleneck, McLean had to strip away the wheels and chassis of his trucks and stack the trailer bodies directly onto a vessel. This required gutting ships to create internal cells designed exclusively for uniform rectangles. He partnered with an engineer named Keith Tantlinger, who designed a 35-foot aluminum box. It was lightweight, yet strong enough to support the weight of multiple fully loaded containers stacked directly on its roof. Inventing a better box was meaningless on its own. They had to construct an entirely new mechanical world, standardized truck beds, specialized cranes, and locking mechanisms, all designed to receive that exact shape. For McLean's new fleet, Tantlinger designed cell guides, vertical steel strips that ran deep into the holes. These created a honeycomb structure that allowed containers to slide perfectly into place and stay secure even in rough ocean swells. This diagram shows the twist lock, a specialized fitting locking into the standardized corner castings, securing two boxes vertically in seconds. These same castings allowed a mechanical spreader bar to drop from above, engage all four corners, and lift the container instantly. This mechanization created an assembly line speed at the docks. A crane could pull an incoming container off the ship and instantly drop an outgoing box into the empty cell on its return swing, replacing manual labor with a continuous mechanical loop. The financial result was immediate. Loading loose cargo cost nearly $6 a ton. Under the new system, that cost dropped to exactly 15 cents. McLean successfully constructed a friction-eliminating machine that turned ports into high-speed factories. Because shipping became nearly costless, factories no longer needed to sit next to urban ports. This shift liberated manufacturers to relocate anywhere land and labor were cheaper. The dense waterfront communities that defined port cities for centuries emptied out. They were replaced by massive, automated concrete hubs located miles away from city centers, operated by a tiny fraction of the old workforce. This highly reliable conveyor belt allowed companies like Toyota to develop just-in-time manufacturing. Instead of paying to store inventory, they could trust that specific parts would arrive in a container at the exact hour they were needed. The eradication of transport friction allowed developing nations to aggressively enter the global market, leveraging lower production costs to become the manufacturing powerhouses for the West. The shipping container acted as a technology that broke and rebuilt an entire industry, altering global labor markets and shifting the center of economic power. This transformation required no advanced materials or futuristic science. It was achieved through the absolute standardization of logistics. A steel box is aggressively mundane. It has no moving parts and lacks the flash of a digital gadget, yet its impact reaches a planetary scale. The most significant innovations often arrive as simple utilitarian standards that possess the logic to scale and wrap the entire globe.